Okay, so while they're trying to get my computer working, I'm going to be talking about behavior. And so basically what you do affects the spread of disease. And I wanted to show you some of the things that I do that hopefully affects the likelihood for me getting infected. I always carry a hand sanitizer, Clorox wipes, and tissue paper. And so I travel a lot, and at least once a month. And before I sit on the airplane, I usually wipe the seat with the Clorox wipes. And if I go to the bathroom while I'm on the plane, after I wash my hands, I usually use hand sanitizer because the water that they have on airplanes is not the most, I don't know if I should say clean water. And so I just, just for precautionary purposes, I always carry my hand sanitizer. But the hand sanitizer, I use it all the time, regardless of whether I'm on an airplane or not. And another thing that I do is I carry a face mask with me, which I forgot to bring right now because I had it in my luggage. And so if there's someone that's like, visibly sick or sneezing a lot on the plane, I put my mask on just because I work with infectious diseases, and I just want to prevent myself from getting infected. And so it's worked. I know a lot of people that once they travel, when they come back, they said, "Oh, I think I got something because now I'm sick." And I probably once in my lifetime I got sick from from an airplane. But I think doing some of these things could actually affect my likelihood of getting infected. And so there are many things, there are many behaviors that you can actually do. So I'm gonna talk about influenza, and influenza is transmitted from person to person. So basically, if everyone could potentially get infected, unless you don't have any interactions with people, then you don't really have to worry about getting infected with influenza. But since influenza is transmitted by coughing, when you're talking to someone, you need to worry about people in general. So there's been a lot of encouragement for people to use their elbow when they're sneezing. And so if you go like this, you're not coughing. Okay, great.
It's only back here.
So if you go to the top, it should be the first one. Yeah. Okay. Woohoo! Yay! Okay. So there's my email in case you guys ever want to email me and ask questions, or if you're interested in summer opportunities or whatever. Okay. Okay, there. Okay, I got it. I think. Oh, did you do it or? Okay. So okay, so I was talking about flu and spreads from person to person, and it is important because it kills people. So it kills between 3,000 and 49,000 people every year. So although most of the people here in the room are not in those categories of people that are more likely to die, we could still potentially die. So can you go to the next one? So here's a picture that I took from a magazine about the different pandemics that we had throughout our history. There's the one in green. Let's see if this works. The circle in green is the 1918 pandemic, and it killed between 50 and 100 million people around the world, and so that is very scary. And then you see two other green circles in 1957 and then again in 1968, and so those two pandemics were kind of mild, and so they didn't kill a lot of people. However, there's the potential for a new pandemic that's going to come in the future. And that's where the red giant circle is illustrating. And many people predict that between 180 and 360 people could die of the next pandemic. So therefore, it's very important for all of us to try to understand the dynamics of the disease and also try to do something to mitigate it. So I'm a modeler, and modelers are very powerful tools, and they can provide all kinds of different answers to a lot of our questions. So decision support. Mark was talking about how many policymakers need to make decisions. They need to know how many vaccines we need to make, who should be vaccinated, and that's where models come into play. Cost benefits, science-based planet. Money is always very, very important. So if you can provide a dollar amount next to your answer, then policymakers are more likely to listen to what you have to say. They provide a range of possible outcomes. You can quantify assumptions and uncertainties. Infectious diseases are very uncertain. A lot of the times we don't really know what's going on, and so there's a lot of uncertainty, but our models are able to capture that uncertainty, and so you can provide a more reasonable answer to policymakers. And they also assess the value of improved situational awareness. So we can say, well, if we start vaccinating, then how that's going to affect the spread of disease. So models are very powerful, and they can help us answer a lot of questions. So these are some of the questions that I'm interested in understanding. The mechanisms for the spread, how social landscapes impact disease evolution, and optimal intervention strategies. But the one that I'm going to talk to you today is about behavioral changes and how they impact disease spread. So these are some of the behaviors that I'm interested in understanding. Sneezing into your elbow, hand washing, using face masks, covering your face when you sneeze, instead of just sneezing into someone's face, or staying at home. Staying at home is also it really impacts the spread of disease, because if you stay home, then you're limiting the number of contacts that you're having, so that's a very powerful tool. And then there's other behaviors, which I'm not going to talk to you about today. And although flu is made out of human, pig, and avian components, today I'm just going to be talking about person-to-person contact and not human and animal contact. So, but I really like this picture because it tells you a lot about behavior and how it's a different kind of behavior, because this is the parents taking the time to take the picture, and instead of removing the kid away from the pig. And so I don't know, I think I would have wiped that kid's mouth with a Clorox wipe. But anyway, okay, so I'm not going to be dealing with this behavior today. Okay, so there are many different types of models that we use. We use, so the models that Mark was describing today are the ones all the way at the bottom, where is the traditional differential equation type models. And then as you increase the level of resolution to your models start becoming more expensive from the computational point of view. And then we have agent-based models, which are simulations that are also able to capture the spread of disease. And so on the right-hand side, you can see the computational cost. Mark was showing you how to run a model on his laptop. And however, some of the models on the top, they have to run on supercomputers, because they're so expensive that you can't really run it on a laptop. And so I'm going to show you an example of a traditional ODE, and then I'm going to go all the way to the top and show you an agent-based model and how we're using supercomputers to model the spread of influenza. Okay, so this is a model that's similar to the one Mark presented earlier today, which is a susceptible, exposed, infectious, recovered type model. And one of the things that I was interested in understanding was the impact of face masks on the spread of influenza. So basically, we have broken up the population into these 5 stages, but then we can also add another box and say, well, what if people wear masks? So then you just include another box that has a subscript M, and so you're assuming that some of the susceptible people are going to wear masks. And then the same thing you do for the exposed population. You assume this, a fraction of them are going to wear masks, and the same for the infected people. And then I have arrows going back and forth because if you try to eat with a face mask, you're not going to be able to. So therefore, you're going to take your mask off. So that's why we have this back and forth movement, because people wear their face mask and then they take it off to eat or to do other things. And also, people don't typically wear face masks at home. And so that's another thing that you need to consider. And so that's why we're removing, where we have this movement. And so basically, the previous model, you can write a system of differential equations to describe that system. And then once you do that, then you can run your model. You can use Berkeley-Madonna to describe the model. And then these are some of the results. So we decided to experiment with different percentages of people wearing face masks. The one on the left says 10%, the one in the middle 25%, and the one on the right is 50%. So we just said, okay, what happens if 10% of the population wear face masks? What if 25%? What if 50% of the population wear face masks? And so you can play with different what if scenarios, and you can also change the effectiveness of face masks, and that's why I have different lines. I have one that has no mask, which is the blue line. And then I have black, red, and green representing different effectiveness of the face mask. Face masks tend not to be very effective for flu because the particles that make flu are very, very, very tiny that they go through mask. However, I've actually experimented this. I had strep, and so I was wearing a face mask when I went to see my doctor. And people would just avoid me because there was this like a radius around me when people saw me wearing a face mask. And so the face mask may not be very effective in terms of keeping the particles in, but it will be very effective in keeping people away from you. So if you are working on like a deadline and you don't want people to disturb you, you should put a face mask, and it's going to be really effective. No one is going to try to talk to you or anything. They're like, okay, hi, bye. So that's why we're experimenting with different effectiveness of face masks. And another question was, who should wear a face mask? Should an infected person wear a face mask? Should a susceptible person wear a face mask? We didn't really know who would be more effective in terms of wearing a face mask. So the blue line is only infected people wearing infectious people wearing face masks. Then the black one is susceptible and exposed, and then the red one is everybody. And so it was very interesting, an interesting result to see that basically everybody should be wearing a face mask. If only the infectious people wear face masks, it's not going to be very effective. So if you really want to make an impact on the spread of disease, everybody should wear face masks. Okay, so the previous model, I was just showing you what if scenarios. You know, what if 10% of the population? What if infectious people? Well, it turns out that it doesn't really work that way in the real world. There's certain people that are more likely to wear face masks. It's not just 10% of the population or 25% of the population. Or there are certain demographic factors that contribute to someone changing their behavior and adopting precautionary behaviors. So one is age. Older people tend to adopt precautionary behaviors more than younger people. Gender, women tend to take more precautionary behaviors. Ethnicity and educational level. And so basically, our model is very simple to capture all these different demographic factors. So if I wanted to incorporate age, okay, then I have, you know, there's people that are up to 100 years of age, so I need 100 boxes. And then, okay, if I want to incorporate gender, then that's 200 boxes. If I want to incorporate ethnicity, then you can just see how the level of complexity is increasing, and therefore I'm going to have, you know, this room full of boxes in order to describe behavior. And so therefore, doing it with a system of differential equations is not very attractive, so therefore we decide to use a computational model, so a simulation. So can you click on the picture so that the movie can start? So this is sort of a movie of the type of simulation that we use, and if you're familiar with SimCity, it's sort of like a SimCity type simulation. Basically, you have buildings, and you're representing all the cities within the United States, and you have people moving and going to different places, and you can actually keep track of everybody in your simulation, and you know their name, their age, their destination, their income, and everything. So this is basically the platform that we use to understand infectious diseases. So there are 4 key elements in our simulation that we're using. One is locations. Everything is geolocated. We have the entire United States. Population, not just the population, but they have to have demographic characteristics, so age, gender, schedule of activities. Everybody has an itinerary, and they know what they have to do every day. They have to go to school, they have to go to the mall, and etc. And then we have disease. So only with these 4 pieces of information, we create this giant simulation that runs in a supercomputer. And so once you create your simulation, you can start extracting very interesting information from your simulation. This is the contact network that emerges from our simulation, and so basically we can see how many contacts everybody has. And so on the right here, I have the contact distribution. And so basically, if you're on the x-axis, I have the number of contacts, and on the y-axis, I have the number of people with those many contacts. So if you see, the majority of people have less than 25 contacts a day in the simulation that I'm showing. And very few people, less than 10 people, have hundreds of contacts a day. So that's very interesting because, as Mark was telling you before, the number of contacts will actually also help you understand how disease is going to spread. And so knowing the number of contacts is crucial for disease dynamics. However, contacts is just one piece of information. The other piece of information is duration. The more time you spend with an infected person, the more likely you're going to get infected. So, so we have a distribution of contact durations on the left, and basically the majority of contacts are less than 30 minutes in our simulation. However, there's a bump there on the 8-hour time, and that's because a lot of people work for about 8 hours, and so then it kind of makes sense to see this 8-hour bump in our simulation. So we're using contacts and duration to describe disease dynamics. And from our simulation, we can also extract these matrices. And here I have people going up to 90 years of age, and you can see how children, which are less than 18 or so, they're red because they're having a lot of contacts, and so that's one of the reasons why they're also a source of infection. And then you can see how people that are older have wider number of contacts, and then you see these 2 arms that are coming out of the giant box, and that's because kids are having contacts with their parents. And so this is all talking about how even if you protect the parents, you can protect the children, or if you protect the children, you would also protect the parents. And so there's a very interesting dynamics here that you can use to understand infectious disease behavior. So in our simulation, this is the only equation that I'm going to show today. This is how we compute the probability of becoming infected. So basically, you're in a room with a number of people, and so you have to compute the probability that each person is going to infect you. So that's the product of all infected people in a location, and then you can determine the probability of a susceptible person getting infected. And so this is a little bit different than what Mark presented, but this is how you do it in a simulation type platform. Can you click on the? So this is this is how we are simulating the spread of influenza. And at the bottom, I'm showing where the infections are being generated. And I have in purple home, in orange work, and in blue school. And so you can kind of see how the majority of infections are generated at home, and they're also at the beginning you can kind of see that work. There's a lot of infections generated at work. And so the reason why a lot of the infections are generated at home is because we spend a lot of time with our families, and so the duration is very important for disease spread, and so therefore we can kind of see how the infections that are generated at home are the greatest. And also, so first, in the previous slide, I just showed you for the entire United States, and here you can kind of take a closer look at what happens in different places. So this is Southern California, if any of you are familiar with. And if you look along the shore, you can see where Beverly Hills is, and interestingly enough, it has less than 17% percentage of population being infected. So the attack rate that I'm showing there is the percentage of people that are infected. And it was very interesting to see that there were these hot spots that were emerging from our simulation. And we wanted to understand why there are certain areas that have higher infection rate versus other areas. So we took some correlations, and the first thing that we thought, oh, maybe it has to be population density, which is all the way on the left. And so we said it has to be population density. However, the R-square for population density was about 0.18. And so that's not a very good number. So then we decided to say, okay, maybe it's the number of children in the home that are important for disease transmission. And so that's the next one. And the R-square was 0.55, which is that's telling you that there is some correlation between having children at home and the attack rate, or the percentage of people that are infected. Then we looked at income, and income also has an R-squared of 0.55. So that's also telling you that there's some kind of correlation between income and attack rate. And then finally, we looked at average household size, and the R-square for that was 0.81. And so basically, the size of your household can actually be a predictor to tell you how many, the percentage of population that will be infected in a certain area. So household size is strongly correlated with attack rate, which I think is interesting. And you can use this result to provide policymakers with how they can use limited resources. You can say, well, if you have limited resources, why don't you just use them in areas that have a high household size, because then that will reduce the number of infections in a population. So because we have this massive computer simulation, we can do all kinds of things, because we have schools, we have workplaces, we have malls, we can do whatever we want in our simulation. We decided to play with school closures. And on the top, I have an epidemic with no interventions. But note that the y-axis is 10% for A, and it's 3% for the bottom three graphs. So we decided to see what happens if you close schools for 5 months. And that's figure B. And once you close the school for 5 months and then you reopen them, you see another wave of infection. What if you close them for 8 months? And so you can see also that there's a long time before you actually generate another wave of infection. And then last one is, what if you close them for 11 months? Which, in my personal opinion, I think school closures are not a good option, because you would have to close them for an entire year, and so you would make all the parents crazy. So school closures are just not a great idea. And here I was playing with months, but we've also tested, closing the schools for 2 weeks, and you can see that as soon as you reopen the schools, because there's still people that are infected in the population, you're just delaying sometimes the epidemic peak. And so relaxing interventions, it's not a good option if you're if you still have infected people in your population, so you will generate secondary waves of infection. So in addition to seasonality, like Mark showed, you can also, by relaxing interventions, you can also generate waves of infection. And this is on the effective reproductive number is shown on the top, and the epidemic curve is shown on the bottom. And so this is basically what's happening. The black curves show you an effective reproduction number for an epidemic where you're not implementing any interventions. So you see that for influenza it's around 2, and so as the number of susceptible people starts to decrease, you can see they are going under 1. Okay, but on the blue curves, you can see that you start with an R effective of around 2, and then you implement fear-based isolation, which means what if people are so fearful of getting infected and that 50% of the population are going to stay home, which is also very unrealistic, but we just wanted to understand the impact of people staying home and being fearful to an epidemic and how that affects the epidemic. And so if people stay home, you can see how you dramatically decrease the R effective under 1. And so then, the levels of infection are very low, so people say, oh, okay, the epidemic is gone, so let's just go out again. And so then they relax that intervention, and then you can see how the R effective slowly starts to increase and goes over 1 before it goes down again. So you can clearly see how interventions affect the effective reproductive number and bring it under 1, and if you relax the interventions, you can bring it over 1 again. So this is also, I'm just showing you the contact network for different interventions. I showed you earlier the red line, which was just the contact network for a population without any interventions. But if you close schools, or if you implement this fear-based home isolation, I have here on the box how you can reduce the number of contacts. You can go from 22.5 to 19.9 if you close schools, which doesn't seem to be very effective, to 8 in the fear-based home isolation. So all these interventions are actually affecting the social contact network, and so therefore, if you have less contacts, your likelihood of infecting people is going to decrease. So here I'm just showing you some other, because now we have a more comprehensive simulation, we can also experiment the impact of face masks using different age groups and ethnicities and gendered, and you can see the blue line is showing you an epidemic for people that wear face masks, and the red one is an epidemic for people that don't wear face masks, and so clearly they have a significant impact on the spread of disease. So in conclusions, policymakers are turning to epidemic models to answer a lot of questions, so this is the perfect time for all of you to get into this field. Mathematical and computational models provide real value. They provide decision support. And if you've seen the movie Contagion, you can kind of see how they use mathematicians and epidemiologists and biologists to kind of solve a major problem. So if you haven't watched the movie, I highly encourage you to watch it. And understanding human behavior is crucial for accurately modeling disease spread, because if you assume that people don't change their behavior, you're going to be overestimating the impacts of disease spread. But if people like me are using these things to minimize their spread, then you're definitely going to make a significant impact on disease spread. And finally, if we don't want if you want to mitigate this impact, then you should really consider doing something for influenza. Thank you. Do you have any questions?
Yes, my name is Fabiola Arroyo from the University. My name is Fabiola Arroyo from the University of Washington, and so I'm really interested in how we can already predict this early that 180 to 300 million people are expected to die from a future pandemic. And so I was wondering how we can predict this early, and if you were like studying the trends and the mutations or the resistance of the bacteria, and what are we doing about it since we can kind of predict it now?
The predictions about the 180 to 360 million, they basically, based on what happened in 1918, they are projecting, based on population growth and contacts, and now that we're highly connected, a person in China can be infected now and then they fly to United States or anywhere else in the world, and you can spread disease a lot rapidly than the kinds of transportation means that we had in 1918. So that's why, that's how they project those many people. But that's in the absence of interventions, which is not realistic, because now we are more familiar with the disease, and so we are actually being more proactive. We have a vaccine that, even though it may come in late, you can still, implement a lot of different interventions. So this is a prediction in the absence of any interventions and people not changing their behavior and all that kind of stuff. So for modelers, I think that number seems quite high, because obviously we're gonna, if there's a new highly pathogenic outbreak, we will try to do everything and anything to mitigate it. And about antibacterial or resistance, there is a lot of research that is currently being done on how resistance to different antivirals and also bacterial type medications could potentially impact the spread, but I think there's a lot to be done in the resistance space, because I don't know that we have a very good understanding of what's generating this resistance and how we can mitigate it. So there's a lot of work to be done in that area.
One more question, and then we can ask questions at lunchtime as well.
Okay, sure.
All right. Kelly Drews, Virginia Tech. I was wondering, have you ever done models that simulate what would happen if you shut down like the interstate highway system or grounded all flights to see what would happen?
We've done it for flights, but in our simulation, of course. And so for like border closures, it's a very it's a very interesting intervention, because it will have a huge economic impact. And so closing airports or closing borders, it's always, a very sensitive topic. But the problem with influenza is that a lot of people are, once you're exposed, you're in an incubating period, so you don't show any symptoms, you don't have any fever. And by the time you close the borders or airports, a lot of people would have already gone through, through your borders, and they would infect people even if you close the borders. So I think closing borders or shutting down airports may not be very effective for influenza because of the incubation period. And so therefore you have a lot of people that are already infecting people without you knowing. And so, but we have done some analysis in that area.